Welcome back. I'm Professor Andy Gunawardena, and today we are going to discuss an exciting topic called classification through logistic regression. So what is classification with logistic regression? It is a method used to predict categorical outcomes, typically binary, by modeling the probability that an instance belongs to a particular class. This approach is commonly applied in scenarios such as determining whether an email is spam or not spam, predicting the likelihood of a disease being present, or any situation where the outcome is categorical. Logistic regression is straightforward, interpretable, and effective for many binary classification problems. First, let's compare linear regression and classification. Linear regression models a function that maps features represented by x with d dimensions to a real number output y. In this process, we're finding a function that fits the training data well, making it possible to predict continuous values based on our input features. Classification, similar to regression, predicts an output, y, but here y is categorical. In binary classification, y can take one of two values, such as -1, +1, or 0, 1. In multiclass classification, y can belong to one of multiple classes, like 1, 2, ishi, k, where k is the number of categories. Classification tasks in machine learning help us make decisions based on categories. For example, email classification distinguishes between spam and not spam, e-commerce transaction classification detects fraud, and tumor classification determines if a tumor is benign or malignant. Often, we use encoding to represent categories numerically, like assigning negative a value of 0 and positive a value of 1, making it easier for algorithms to process these distinctions. A well-known application of classification in machine learning is diagnosing whether a breast tumor is benign or malignant, as studied by Street et al. In 1992. In this setting, a doctor extracts a fluid sample from the tumor, stains the cells, and outlines them, often with the aid of image processing to refine the outline. The system then computes several features for each cell, such as area, perimeter, concavity, and texture. For these features, it calculates statistics like mean, standard deviation, and maximum values to help make an accurate diagnosis. Here's a breast cancer data set. It contains many features, X, that can be used to predict if a tumor is malignant or benign. First, we have to learn from data what features can help predict Y to be 0 malignant or 1 benign. Of course, we can use all the features, but that would be computationally expensive. So, first, let's find out if there are some features that are more predictive than others. Say, for example, we plot only the mean area and mean hash of concave points and color code the cells as red or blue. There seems to be a clear divide in benign and malignant tumors. Hence, these two features can be a good predictor. We can certainly add more features to increase the predictive power. But for now, we will stick with two features. Now the question comes to, how can we find the line separates the two types of tumors? We need to develop a mathematical model to understand this. Now the problem comes down to determining the boundary that separates the two types. Just guess the equation of the separation line. If we assume hex t equals sign -8 plus 16x, 1 plus 10x2, and later we will show how to find the coefficients. Here's another example where we can predict the pass-fail status based on where the separation line is. Can you draw the separation line and find a formula? Next, we develop the notation and mathematics to find the logistic regression line.